Today we'll do LU, PLU, and Cholesky decompositions. Now you guys must be familiar with Gaussian elimination. That's basically the same thing as LU decomposition, and we'll look at the algorithm for LU decomposition. And then I'll skip through PLU. I'll just tell you what PLU and Cholesky decompositions are without going through the algorithms. So this is, we begin with LU decomposition. Excuse me. Take a matrix, a square invertible n by n matrix A. LU decomposition is the decomposition of this A, or factorization of A into a lower triangular matrix and an upper triangular matrix, so that A equals LU. That's LU decomposition. A is the given matrix, and we factorize or decompose into a lower triangular and an upper triangular matrix. Visually, this is what it looks like. A equals LU. We'll begin with a simple 3 by 3 matrix example, and we'll focus on how to convert this using row operations into a upper triangular matrix. So, step 1, we eliminate column 1 from row 2 and row 3 using R1. And then step 2, we eliminate column 2 from row 3 using row 2. So here's what I mean. I use R1 to eliminate column 1, that is to convert these 4 and these 2 4s to zeros in the second and third row. And I use the first row. And in the next step, what I do is, this is where it's shown. So this is what I do. And in the next step, I use this matrix here, and I eliminate column 2 from row 3. This is row 3, column 2, using, now this time I'll use this row instead of the first row. Okay. So, numerical example. Step 1, first I want to eliminate this 4 using row 1. What should I do? I just subtract 4 times row 1 from row 2. So row 2 becomes R2, row 2 minus 4 times R1. So this 4, 4, 2, I subtract negative 4 times row 1, which is 1, 2, 2, and I get 0, negative 4, negative 6. So I'll end up with this matrix. This is the new A. Now my goal is to eliminate this 4 here, again using this row 1. We're still in step 1. So eliminate R3, 1 using row 1. So what I do is this. R3 equals this R3 minus 4 times R1. And I get this matrix here. So I have completed step 1, which is reducing these to zeros. The first column, these entries, in the second and third rows to 0. Step 2 is next. Now here, I'll focus on eliminating, zeroing out the elements from column 2. In step 2, I will use row 2 to eliminate some columns below it. So row 3 only. So This is my goal, to eliminate A32 using R2. So what should I do? This is -4, this is -2. If I multiply this with half and subtract it from row 3, then I would get my 0 here. So I do R3 equals R3 minus half R2. This is the operation, and my row 3 becomes 0, 0, -1. So this is now the new matrix A. After I've completed steps 1 and step 2, and what do you see here? The lower triangular elements of A have been reduced to zeros, so I'm left with only an upper triangular matrix. What are the eigenvalues of an upper triangular matrix? By the way, pop quiz, the diagonal elements. The determinant is the product of the diagonal elements for an upper triangular matrix. So upper triangular and lower triangular matrices are quite easy to handle compared to a regular matrix. Okay. So this is what I did. I used, what we're doing now is, so we went through this set of operations, and now let's see what we did in terms of matrices. So this was the original matrix that we had. And then I took this matrix and I converted it to this matrix here in step 1. So this is this matrix here. Now observe what I do. It's the same thing as pre-multiplying the matrix with this matrix here. I take this, how do I construct this matrix here? The previous row operations are equivalent to multiplications with lower triangular matrices. That's my goal now to explain. So look at this matrix here. 1, 0, 0 is in the first row, and so first row here was multiplied by 1, second row and third row with zeros. And so the first row is intact. Next, the second row is multiplied. So this is the second row of this matrix. Or I take this second row and multiply with all of this matrix. And so what I'm doing is the first row is getting multiplied with -4, the second row with 1, and third row with 0. And then we land up with this here. So this -4 is because I was subtracting 4 times row 1 from row 2. Okay, that's why I get this -4 and 1 here. Next, what I do is I take row 3 here, and then I see that I'm multiplying row 1 with -4, row 2 I just ignore, multiplication with 0, row 3 with 1 to get this 0, -2, -4. And so what I did, these two operations were equivalent to pre-multiplication with this lower triangular matrix. And I therefore got zeros as these two elements here. Okay, and let's call this M1A. Okay. Now, this is the general case. What I do is, step 1, I eliminate column 1 from row 2 and row 3 using row 1. So R2 is R2 minus. I scale up my R1 so that A11, after it's scaled, becomes equal to A21. Okay, so this is the scale, and I subtract the scaled version of R1 from R2. And then I do the same thing with row 3. I scale R1 using A31 over A11 as my factor, and then I subtract the scaled R1 from R3 to get my new R3. So this is what I did. That's equivalent to pre-multiplication with this M1 matrix, which is a lower triangular matrix. So what's happening is, so this is step 2. Did we go through step 2? No, earlier did we go through step 2? Sorry about this. Yeah. Step 2, this is what we did. And we landed up with a lower triangular matrix. And now let's look at the equivalent pre-multiplication with a matrix. So this is the matrix M2 that I pre-multiplied the new A with to get this. So this is the first row, 1, 0, 0. That's why I get 1, 0, 0 here. Excuse me, 1, 2, 2 here. 1, 2, 2 is repeated here. Then 0, 1, 0. So 0, 1, 0. This 0, negative 4, negative 6 is repeated. But here, what I did was, again, observe that this is a lower triangular matrix. And so I'm doing this matrix operation. I'm subtracting half of row 2 from row 3, which is from this, and then I get my 0, 0, negative 1. And again, like I said, this is a lower triangular matrix. And this is an upper triangular matrix. So what I did was, I took my A here. This is after step 1. This is step 2. I took my A, pre-multiplied it with a lower triangular matrix, M2, and I got my desired form of A, which is a upper triangular matrix. Okay, so this is the end of my LU decomposition for this little 3 by 3 matrix. So this is what I actually did. This is this R2 is scaled up so that it matches A32 here. A12 matches up with, A22 matches up with A32, and then I subtract it from row 3. This is the generic operation that I did. And that's equivalent to A is replaced with M2 times A. So this is what I did. This was my original matrix here, this. Pre-multiplication with lower triangular matrix M1 gave me this. And then I took this matrix here, which is M1A, and then I pre-multiplied M1A with this lower triangular matrix M2. And then I got my upper triangular matrix. Okay, so overall, this is what I did. This is the original A, and then this is multiplication, pre-multiplication with M1, and then pre-multiplication with M2. Never forget the sequence of operations. And then I get my upper triangular matrix. Now, that's equivalent to pre-multiplication with the product M2, M1, which I call M. Okay, so A was my original matrix, and then MA is this. And this is my M. M is M2 times M1. One interesting fact that you'll observe is this matrix M is also lower triangular. The product of lower triangular matrices is always lower triangular. Okay, something that you need to remember. Now, what in the kth step, now let's generalize. So in the kth step, what we're doing is we eliminate column K from rows K plus 1 through N using the kth row. Rk is the kth row, and I'm eliminating, I'm focusing on the same column K, and I'm doing the elimination on all the rows below row K plus 1 through row N. Okay. So this is the equivalent operation that I'm doing. Ri, for every I below K, I replace Ri with Ri minus aik over ak times rk. And this I has to be below k, therefore I is k plus 1 through n. That's equivalent to, this is the kth step, pre-multiplication of A with a lower triangular matrix Mk. And Mk is lower triangular. This is visually what you look at. This is the initial matrix. Step 1, I use row 1 to eliminate all these lower elements from column 1. This is step 2, and this is right before step k minus 1. Step k, I eliminated this. Okay, sorry, this is step k minus 1, right after step k minus 1. And then this is step k. So in step k, what did I do? This is step k minus 1, and just the one before my general step k. So what's happening here? These elements are getting zeroed out, correct? Now, observation 1, this k should iterate from 1 through what? What's the last step? In the last step, I'm going to eliminate the last but one element using the last but one row. So that's n minus 1. There's nothing below row n, so I'm never going to get a k equals n. So k will vary from 1 through n minus 1. Okay. Now, another thing. This is right before step k. Okay. What am I doing here? Now, do I need to do these subtractions? Do I need to subtract the entire row k from each of these row I below it? No, because we already see that these are zeros. So when you're looking at a really large matrix like a 100,000 by 100,000, it really matters. Okay, so we don't have to waste computer time trying to subtract zeros from zeros when we already know that all these elements are zeros. So we are going to only change using only these elements from the kth column onwards. I'm going to subtract only this part of row k from all these row i's. Okay, so only from column k. I don't have to waste more computer time trying to subtract zeros from zeros. Okay, so this is my step k. All these elements will of course change because I'll scale this portion of the row and then subtract it from all of these. So aik plus 1 through ain all the way up to ann will now have different values after this step. This is the last step. K equals n minus 1. And that's when I have already converted my original A into an upper triangular matrix. So this is the general operation. Row in my kth step, I'm using elements akk through akn, this portion of the row k, and then subtracting, scaling it up, and then subtracting it from each row I below row k. So I must go from k plus 1 through n. Okay, and so this is my basic LU decomposition algorithm. This is the step index. It goes from 1 through n minus 1, and then from now I'm looking at rows below k, so k plus 1 through n, and then I'm doing this operation. And mind you, I ignore the previous columns because they're all zeros already. Okay, so, and this whole thing is equivalent to pre-multiplying A with this sequence of matrices. N minus 1 steps here, K goes from 1 through N minus 1, and so I'm pre-multiplying it with M1, then M2, all the way to Mn minus 1. And each of these matrices, M1 through Mn minus 1, are lower triangular matrices. And after this sequence of operations, A becomes upper triangular. Okay. So I said that the product of lower triangular matrices is a lower triangular matrix. So this Mn minus 1 all the way to M2, M1, the product of all this is M. M is also a lower triangular matrix. Ma equals U. Okay? Where M is the product of all these MKs. Now, M is lower triangular. Now, my question is, well, we did this and we got an upper triangular matrix. So A got converted to an upper triangular matrix. But we'd never stored any of these M's. We never actually constructed these matrices. Correct? So we don't know what these matrices are, really. So how to get these matrices? Or how to get the product of these matrices? Because that's what eventually I want. Ma equals U. That's my first step of LU decomposition. Okay, that's most of LU decomposition. There's one last step. So how do I get my M? What I do is I simultaneously take A and an identity matrix. Okay, and then step 1, the same row operations that I perform on A, I will also perform on I. So, since I'm doing the same row operations, I'm pre-multiplying essentially A with M1 and I with the same matrix M1. That's in step 1. Step 2, I pre-multiply this with, it's equivalent to pre-multiplication with M2. So I take this M1I here, the transformed identity matrix, and then pre-multiplication with M2. I do the same set of row operations that I did on A. I carry out those operations over this M1I, so I get M2, M1I. And then all operations that I do on the A, I'll also do on the identity matrix. And so eventually, this is what this, here I get U, which is MA. M is this product here of Mn minus 1 through M1. And here, this is the identity matrix. So here I get M. Okay. But I've still not performed LU decomposition. I want A should be equal to L times U. Okay, I just got an upper triangular matrix, and I got this M here such that MA equals U. So A must be equal to M inverse U. Okay. The good news is, well, M is lower triangular, and the inverse, which is M inverse, is also lower triangular. The inverse of a lower triangular matrix is also lower triangular. And same applies for upper triangular matrices. The inverse of an upper triangular matrix is upper triangular. Okay, so A equals M inverse U. Okay, L equals M inverse U. But again, what's the point? Because I have to carry out a matrix inversion, right? Well, it just so happens that inverting a lower triangular matrix is much simpler than inverting a general problem of matrix inversion. Okay, you need a simpler algorithm. If you remember your undergraduate days, then it's the back substitution algorithm. Okay. So the matrix inversion algorithm is simpler. So it has lower complexity, and that's why it's easy to, it's not as hard computationally as intensive as inverting a general matrix. Inverting a lower triangular matrix is relatively easier. And so I get L equals M inverse. So that A equals LU. I have accomplished my LU decomposition. Okay, any questions with this before we move on to PLU decomposition? Okay, next is PLU decomposition. Yeah.
So in the example, when we were actually decomposing the matrix into lower and upper matrix.
Maybe this one?
In previous slide.
Yeah.
Yeah, previous. Like previous. Yeah. So at that time, we are also finding M also.
No, we are not. This is equivalent to what we are doing. What we are in fact doing is just this.
Okay.
Replacing the old R3 with R3 minus the scale version of R2.
I got it.
Okay, using this same scale, we got to carry out the operations with the identity matrix. Okay, do you understand now? It's not like we take these elements from the identity matrix separately. No, these same elements, okay? And that's equivalent to this premultiplication.
I got it.
Okay, and if you look at the algorithm, that's what we are in fact doing. This is the algorithm. Okay, and just suppose I had MATLAB here and I implement this algorithm. It's pretty straightforward to implement this in MATLAB. So what I would do is input would be A, and then take an identity matrix I, okay, right here, and then Ri, I'll implement this operation for this A here, and then using the same ratio, I'll do exactly the same operation on the other matrix, which I start off as an identity matrix. Okay, so this is what we equivalently do, and this is how we get the matrix M here, and we invert it to get the matrix L, the lower triangular matrix, such that A equals LU. Okay, now PLU decomposition. Please do raise up your hand anytime you have a question, okay? Or interrupt me if I accidentally don't look. Okay, first let's introduce ourselves to what's a permutation matrix. A permutation matrix looks very much like an identity matrix, shares some of the properties of identity matrices. It has a single one in every row and every column. Every row there is a single one here. Okay, and it's equivalent to taking an identity matrix and then row 2 of the identity matrix comes here, then row 4 of the identity matrix, observe this here, then row 1, and then row 3. Okay, so I take an identity matrix and rearrange its rows, I'd get a permutation matrix. Or I equivalently could have rearranged the columns. Okay. So a permutation matrix has a single one in every row and every column. The inverse of a permutation matrix is its transpose. Okay, now if you want to, well, I haven't gone there yet, sorry. I'll take it up later. So P inverse is simply P transpose. Okay, and I take this matrix here, and this is its transpose. You can see that P times P transpose equals the identity matrix I. The determinant of a permutation matrix is 1. Products of permutation matrices are also permutation matrices. So in other words, if you permute the rows and then again you permute the rows, it's equivalent to one single set of permutations, right? So product of permutation matrices are permutation matrices also. Now, what does pre-multiplication of any matrix A with a permutation matrix look like? So this is my matrix, the permutation matrix. This is my matrix A. What do I get here? I have basically rearranged the rows of this matrix A. Okay, so pre-multiplication with a permutation matrix is equivalent to rearranging the rows of the matrix. Equivalently, this is something I wanted to tell you, post-multiplication with P transpose, okay, if I take A, ignore this here, I take P transpose and I post-multiply it with A. Then that would be like rearranging the columns of my A in exactly the same order. Okay. So for rearranging rows, pre-multiply with a permutation matrix. For rearranging columns, post-multiply with the transpose of a permutation matrix, which is a permutation matrix too. So P times A is row reordered A. Okay. Now suppose this is my A. And I want to do LU decomposition on this using the algorithm that we just saw earlier. Why can I not apply this algorithm right away? Why can I not do LU decomposition right away? Because right here you see a 0. I cannot scale this so that this becomes a 2, a 1, and a -1 and then subtract it from the first column. Okay. Sorry about that. So, LU decomposition cannot be applied as A11 is 0. So, I apply this permutation here. What I do is pre-multiply my A with, let's say, P prime. And now I get this. Now I can use this 2 here to reduce all of these to 0 as well. This is already 0. Okay, and so now I can apply my LU decomposition. So this is my P prime A, where P prime is a permutation matrix. And this is what I get. And then now I can apply my LU decomposition to this one. And so I get P prime A equals LU. Whence A equals PLU, where P equals P prime inverse. It's basically I'm pre-multiplying both sides with P prime inverse. Okay. And I just said that did I say this, that the inverse of a permutation matrix is a permutation matrix? I didn't say it directly, but I said that the inverse of a permutation matrix is its transpose, right? And the transpose is again a permutation matrix. So this is basically the transpose of P prime. P is the transpose of P prime. That's it. Okay. Now, when you apply the PLU algorithm, that would be like pre-multiplication with a sequence of permutation matrices. But, so this is what the algorithm would have done. Okay, before doing the LU decomposition, it would have seen a lot of things and pre-multiplied it with all these matrices. Okay, and this is equivalent to, so pre-multiplication with all these matrices is equivalent to, since the product of permutation matrices are permutation matrices, so that's equivalent to some permutation matrix P prime such that P prime A equals LU. Whence A equals PLU, where P is transpose of P prime. Okay, so this is PLU decomposition. Any questions with this? Did you do this when you guys did Gaussian elimination undergraduate? I don't know whether it's taught or not, but you did. Linear equations. This is one application, a numerical application of LU decomposition or PLU decomposition. We need to solve AX equals B. A really big matrix A, a square matrix A, but a really big one. Okay, and so what we do is we do the PLU decomposition of A, and we get P, L, and U. It's a single MATLAB command, by the way. PLU. PLU with argument A, it will give you P, L, and U. Now, since AX equals B, so PLU X equals B. Or X equals U inverse, L inverse, P inverse, B. Now, inverting all these matrices are straightforward. P inverse is basically P transpose. L inverse, L inverse, U inverse is back substitution, and L inverse is forward substitution. Okay, and you guys learned back substitution, forward substitution in your undergraduate days. So this is how we can solve a set of linear equations. Now, of course, in MATLAB, it's much easier. All you have to write is X equals B backslash A. Okay. Okay, so this is my X here. And inverting L and U are easy as they are upper triangular and lower triangular. Okay, now the determinant of a lower triangular or upper triangular matrix is the product of the diagonal elements. So this is the determinant of a lower triangular matrix. This is the LII, are the diagonal elements. I take the product, get the determinant. Likewise for the upper triangular matrix. Okay. So what we can do is, suppose we want to find the determinant or the inverse, we can apply PLU decomposition. A equals PLU. The determinant of A is therefore determinant of P. P is a permutation matrix, so its determinant is 1. So the determinant of L and the determinant of U, all you have to do is take the products. A inverse is, like I said, U inverse, L inverse, P inverse. Any questions with this part? It should be fairly easy. Cholesky decomposition. Now, Cholesky decomposition is applied to a positive definite matrix, and we'll see how. Okay. So this is Cholesky decomposition. Yeah?
This PLU and LU valid if A is a full rank matrix?
If A is a
Full rank.
No.
Okay, for no solution and infinite solution, still
You can get it. I'm trying to think mathematically what it is, because you cannot solve it this way. You cannot solve it this way, right? Because either L or U might not be invertible. So what you would do is, well, you can transform that to, you can reduce the number of rows a priori and then apply PLU decomposition. Okay, but there are more sophisticated methods, and I'm going to go through those later on in this course. Cholesky decomposition. And by the way, when A is not full rank, it's a square matrix, so it's obviously not full row rank. Okay, so in that case, instead of the inversion, you take the pseudo inverse. We will do that, I think, in the very next lecture after this or the lecture after that. Okay. So we'll be covering that, but a better way to, or you can learn about it beforehand by looking at another YouTube video that I have. Okay, it's called pseudo inversion of a matrix, or matrix pseudo inverse of overdetermined and underdetermined systems. So what you asked is an underdetermined system. Okay, but we will be covering that too. So here the assumption is that it's full rank. Okay. Cholesky decomposition, again, I said it has to be positive definite, which means that it has to be full rank. You understand why a positive definite matrix must be full rank, right? Well, that's something for you guys to ponder about. Okay. Matrix must be symmetric positive definite. Now, I've already told you that like when you have a quadratic form, X transpose QX, just assume that Q is symmetric. Okay. If it's not symmetric, then just replace it with Q plus Q transpose divided by 2. Okay. And X transpose times that matrix X will have the same value. Okay, so for all practical purposes, assume that whenever you have a quadratic form X transpose QX, assume that Q is symmetric. Okay, and then the question of whether it's positive definite, negative definite, positive semi-definite, indefinite, whatever arises. So we assume that this is the case. Okay, even if I've not specified, if I say that A is positive definite, it automatically means that I'm assuming it's symmetric. Okay, so A must be positive definite, symmetric positive definite. Whence, this is the Cholesky decomposition. A equals LL transpose. Okay. One way to argue why this positive definite matrix must be full rank is because the eigenvalues must all be positive, right? And so the product of the eigenvalues would be the determinant of the matrix. None of the eigenvalues would be 0. If it's positive semi-definite, then one of the eigenvalues would be 0, one or more. Okay, so that's one way to look at what I just said. This has to be full rank. Okay, A equals LL transpose. This is what Cholesky decomposition accomplishes. A equals LL transpose. L transpose is upper triangular. the transpose of a lower triangular matrix is upper triangular. So this is much like the LU decomposition, with one extra feature is that the U is nothing but L transpose. Okay. So this is the equivalent Cholesky decomposition. Another form, and this is the default in MATLAB, unless you want to decompose A into lower triangular matrices, in MATLAB the default is upper triangular. Okay, so if you just say Chol, C-H-O-L, Chol of A, then it will return U such that U transpose U equals A. You have to pass a second argument, lower. Then it will return L. Okay, so this is an alternate form of Cholesky decomposition, decomposing this A into upper triangular matrix transpose times upper triangular. Okay, which is again LU, a form of LU decomposition, because U transpose is lower triangular. Why do we prefer LU decomposition over, Cholesky decomposition over LU decomposition? Okay, one immediate reason is you can see that we are operating only one L, not a separate L and a U, correct? So that reduces the storage space for humongous sized matrices, and it reduces the number of operations too. Okay, so 50% less storage space. Pivoting is not necessary. Okay, because each time in the actual algorithm, you're taking the diagonal elements and you're dividing some things with the diagonal elements of the matrix. Okay, and so this way you know that the diagonal elements in an intermediate operation, every intermediate operation, the diagonal element will be non-zero, will be positive. Okay, but I'm not giving you the Cholesky decomposition algorithm. Pivoting is not necessary, therefore. And it's faster. It's 25% the number of computations of LU decomposition. But it can only be applied to positive definite matrices. If it's not positive definite, if you apply the algorithm, you'll get imaginary parts. Okay, and if it's not, let's say it's positive semi-definite, then you'll get a divide by zero somewhere if you apply just the basic Cholesky decomposition algorithm. Okay, now why do I say that A must be positive definite? Okay, now let's assume that L and L transposes, therefore they are full rank. Okay, that's because I'm reducing A into this form, right? Just replace B with L. A equals BB transpose, correct? If I do this, if A is equal to some B times some B transpose, okay, if we can factorize A into something of this form, forget L, which is lower triangular, a generic case, B transpose, then it must mean that A is positive semi-definite. Okay, but if, in addition, if I were to say that A is equal to BB transpose and B is full rank, then A is positive definite. Proof. A equals BB transpose, okay, which means that X transpose AX is equal to X transpose B transpose X, which is equal to this. And this is the inner product of B transpose X, correct? This must be greater than or equal to 0. Now, for positive definiteness, for any non-zero X, Okay. For any non-zero x, this must be strictly greater than 0. Correct? Now, this inner product of B transpose X, suppose X is non-zero. When will this inner product be equal to 0? When B transpose, or same thing as B, is not full rank. Right? Only in that case would, if this is not full rank, then B transpose for some non-zero X would be equal to 0. Correct? But for any non-zero X, if this is strictly greater than 0, it automatically means that B transpose, therefore B is full rank. B transpose X is non-zero, which means that B must be full rank. Okay, in which case A is positive definite, not positive semi-definite. And like I said, when we are doing Cholesky decomposition, I'm assuming that L is full rank. Otherwise, Cholesky will give you a divided by 0 error. Any questions with Cholesky decomposition? I didn't give you the algorithm, but it's fairly easy to look at it. It's there in the lecture notes, my lecture notes. Okay, so any questions or? Quick review. So this is the basic LU decomposition. And the reason I went over an algorithm is so that at least you guys can think algorithmically. But all these are automated these days. We don't, unless you're working on something which requires some numerical issues, you don't have to worry about it. MATLAB or Python would do it for you. A equals LU. This is what I do. And in the kth step, this is the operation that I carry out. The equivalent of each of these operations is pre-multiplication with a lower triangular matrix, right? So I get a sequence of lower triangular matrices times A equals the upper triangular matrix, whence MA equals U, where M is the product of all these matrices, whence A equals M inverse U, which is LU. And product of lower triangular matrices is lower triangular. These are all lower triangular matrices. Inverse of a lower triangular matrix is lower triangular. These are things that you should remember, okay? Then, product of permutation matrices is a permutation matrix. Inverse of a permutation matrix is its transpose, which is also a permutation matrix. Determinant of a permutation matrix is unity. And so we can, if we rearrange the rows of A before doing LU decomposition, then we would get something like this. This is P prime, the permuted version of A, okay, which is equivalent to A equals PLU. Determinant of A is simply look at the diagonal elements of L and U, and their product will be the determinant of A. Inverse would be U inverse, L inverse, P inverse, and Cholesky decomposition only for a positive definite matrix, A equals LL transpose or A equals U transpose U. Any questions with this? Go ahead. Any questions related to this? Okay, well, this was a relatively short lecture then. We can end.